Chemistry chapter 22 theory video 4 calculations involving rate constant K. So now we know how to obtain the rate constant, and now we are going to going into detailed calculations which would be a part of your examination paper. So here they have given in the presence of hydrogen ions, hydrogen peroxide reacts with iodide ions to form water and iodine. H2O2 plus 2I minus plus 2H gives you 2H2O plus I2 aqueous. The rate reaction has been given as K H2O2 I minus. So they have given the progress of the reaction followed by measuring the initial rate of formation of iodine. So here the table has given the rates of reaction obtained using various initial concentrations of each reactor. So in the first experiment, H2O2 has been set at 0.02 and iodine has been set at 0.1 and hydrogen is also at 0.01. Then the initial rate is 3.5 into 10 to the power minus 6. 3.5 into 10 to the power minus 6. Then they have increased the H2O2 concentration at 0.03. Then you can see the iodine and hydrogen has been maintained. Then you can see the initial rate of the reaction has increased to 5.30 into 10 to the power minus 6. So that means increase in the H2O2 concentration has affected the rate. Then then they have changed the concentration of the H2O2 to 0.005. That means they have reduced it, but they have changed the concentration of iodine and hydrogen to 0.02. Then it has decreased to 1.75 into 10 to the power minus 6. 1.75 into 10 to the power minus 6. So there is a reduction there. That is because H2O2 concentration has reduced very much. The H plus concentration has increased. The iodine concentration also has increased. So let's see how to use these values to figure out what we need to know. Now to calculate the K, for experiment 1, we write the rate equation. Rate reaction is equation is K H2O2 into I minus. Then we take the K rate upon H2O2 into I. Then we substitute the values and we get K to be 1.75 into 10 to the power minus 2 cubic decimeter per mole per second. So we got the K for that. So this is a very important distinction, how to calculate it. Now here we have disregarded the hydrogen ion concentration because it does not appear on the rate equation. So for hydrogen, the order of the reaction is 0 order for hydrogen, but for H2O2 and I minus, it is going to be order 1. So that is to calculate K from concentrations and initial rate. So whatever the values that they have given, you can figure out K. Then if they give you K half-life and ask you to find K, we have certain relationships that we need to take. For a first order reaction, half-life is related to the rate constant by the expression T half equals 0.693 upon K. T half is the half-life measured in seconds. So we write it K equals 0.693 upon T half. K is equal to 0.693 T half. So this is for a first order reaction. So if you take the first order reaction of cyclopropane to propene, The half-life is 17 minutes. We saw that in the earlier graph. So first what we need to do is we have to convert minutes to seconds, then substitute the values. T is the T is T half is equal to 0.693 upon T half. So we know that it is K is equal to 0.693 upon T half. So T half, that is the half-life. Half-life is 17 into 60. Then we get K to be 6.79 into 10 to the power minus 4 cubic decimeter per mole per second. So if you look at the table 22.1, it will have the same value for K. Now you will not be asked to calculate the rate constant for zero and second order. You will be questioned on for first order only, and that calculation is a little complex. So if we know the rate constant, we can calculate the half-life also by using K equals 0.693 upon T half. So if T half also can be calculated, and K also can be calculated. Now let's go to these worked examples to try and figure out how to use these in our calculations. Now methanol reacts with hydrochloric acid at 25 degrees Celsius. The products are chloromethane and water. CH3OH aqueous HCl, CH3Cl plus H2O. Equimolar amounts of methanol and hydrochloric acid are mixed at 25 degrees Celsius. The progress of the reaction is followed by taking a small sample of the reaction mixture from time to time, then titrating each sample with a standard solution of sodium hydroxide. So they won't give you the rate, they will give you how to find the rate, the data that is needed for you to calculate the rate. At time 0 minutes, it is mole per cubic decimeter. HCl is 1.84. Then CH3OH, it is also mole per cubic decimeter 1.84. Then 200 minutes later, it is 1.45, 1.45. I believe this should be in seconds, but they have given in minutes. I'm pretty sure the reaction is considered in seconds, but not minutes. But let's see whether they have, no, they have taken in minutes. Yeah, so then what you need to do is you have to draw the graph of concentration of HCl against time, and then you draw tangents to find out the tangents to the curve at concentration against time, and then that is the graph that you need to draw, and then you draw the tangent to tangent at different positions to find out at 600 minutes, 800 minutes, 1000 minutes, etc. You draw a tangent and try to figure out the gradient. So from the gradient, the rate of the reaction can be obtained. Now here we have taken in this chart, we have the values at time. Concentration is 1.84. So this is the concentration of what we have drawn is for hydrochloric acid. So the chart, everything else is for hydrochloric acid. So the rate corresponding to HCl has been calculated. Then the rate corresponding to HCl is 1.04 mole per cubic decimeter. So it is going to be to HCl, when the HCl concentration is 1.04, rate is going to be 1.23 into 10 to the power minus 5, because it is 2000 into 60 seconds. So like that you convert, you divide the you divide it by the time to find the rate. You know how to find the rate, and by that you find out the rate from the graph by using the gradient. So then for methanol and hydrochloric acid, you figure out different rates, and thereby you draw the graph showing how concentration in hydrochloric acid or methanol affect the rate of the reaction. So the curve will we draw the curve, and as a result, when you draw the curve, rate of reaction against HCl and ammonia concentration, it will give us the idea that it is most likely to be second order. So in this 22.8 graph, what we see is an upward curve. So that gives us a second order. But to figure out the second order in relation to what, we have to understand, because HCl and methanol concentrations both are reducing. We know that it is second order, but because all of them could be second order. So rate could be either CH3OH into HCl, or KCH3OH squared, or KHCl squared. To confirm the possibilities, we will have to do other experimentation as well. However, what we can say for certainty is that the overall it is a second order reaction. I hope that makes sense. This is a little complicated, but if you try to go through the worked example again and again, you will be able to understand what it is all about. If you have any doubts, please ask me. If you didn't understand my explanation, please ask me, then I will explain it again in a different way. Write down calculations involving the rate constant, calculating K from initial concentrations and initial rate. For below reaction, H2O2 aqueous, 2I minus aqueous plus 2H plus aqueous, giving 2H2O liquid plus I2 aqueous. Rate of the reaction is KH2O2 concentration into I minus concentration. From the data provided in table 22.4 of the textbook, we can calculate K using below steps. We first try the rate equation. Rate equation equals KH2O2 I minus we rearrange it so that K is equal to rate upon H2O2 concentration into I minus When after substituting the values, we get K to be 1.75 into 10 to the power minus 2 cubic decimeters per mole per second. Leave a line and write down calculating K from half-life. For a first order reaction, half-life is related to the rate constant by the expression T half equals 0.693 upon K, where T half, or the half-life, is measured in seconds. So I hope you understood. If you if you understood, please do question number 7. If you didn't understand, please let me know.